Hey everyone, Venki here. This is Lab 2 with lines of charge. The problem was to compare the estimated value of charge of the tapes using experimental data where the tapes were treated as point charges to the value of charge of the tapes using computational Python modeling where the tapes were treated as lines of charges. And then this is to confirm that the lines of charge model is more accurate. So the approach I took was to first finish the program, then determine the number of partitions I would divide the tape object into, input the estimated value of charge, and then compare the resulting electric force on the top tape to the gravitational force on top tape, and then I kept adjusting the charge until the electric force equaled the gravitational force. The materials used for this lab are a roll of clear tape, a ruler, a table, and two stackable objects. So important concepts here, Newton's second law, there are only two forces acting on the top piece of tape, and they are gravity and the electric force from the bottom tape. And these have to add up to zero because the system is in equilibrium as the top tape is not in motion. And Newton's third law, the top and bottom tapes exert equal and opposite forces on each other. Then you have your electric field equation, and then superposition, where you have to sum the electric fields from all pieces of bottom tape acting on each piece of the top tape, and then sum the electric fields at pieces of the top tape to obtain the net electric field at the top tape. And this is really important for the line of charge model. And then you have your electric force equation. So to approximate the charge on the floating tape, you had to treat each tape as a single point charge. And to calculate charge on floating tape using Python, you had to treat each tape as line of charges. And then understanding the line of charges are made up of infinitely small points that each have their own point charge. But for the sake of this program, I use 100 partitions. And the line of charges are oriented on the horizontal x-axis. So I started off the experiment by making U-tapes and seeing how they interact with my hand. The U-tapes attract my hand because the U-tape is negatively charged, and my hand has positively charged salt ions. And then I saw how two U-tapes interact with each other, and they repel each other because they're both the same charge. So after taking a few measurements, such as length, mass of tape, and the distance between the two tapes, and then understanding that the force of the bottom tape on the top tape has to equal the force of gravity on the top tape, you could solve for the charge of the tape by rearranging the equation, and I got 4.67 e to the negative 9 coulombs. So here are the physical constants, and then the mass of the tape, and Q right here is the charge that we just estimated, and then the Q under it in line 28 commented out is the charge that I found after treating each tape as a line of charges with 100 partitions or pieces. And as you can see, both these charges are drastically different, and we'll see later how different they actually look, and I'll explain later why they're different. And over here is your function for calculating electrical field from lab 0. So lines 84 to 85, they create a line of charge for each tape, and then lines 102, 111 for scales. I just played around with it until I got what looked right and seemed reasonable. So this big for loop right here, it starts off by iterating through each piece of the top tape, and then iterating through each piece of the bottom tape to calculate the electric field at the location of each piece of the top tape due to every piece in the bottom tape. And then it calculates electric force, and then it creates an arrow for the net electric field at the top tape due to all the pieces of the bottom tape. And it does this for every piece of the top tape. So now we have arrows to represent the electric force on the top tape and the gravitational force on the bottom tape. So on the left, you have your model with the charge that we estimated, and you can see here that the white arrow, which represents electric force, even with the picture zoomed in, the white arrow is super small, so that isn't right. And over here, the charge I found by trying again and again until the electric force equaled, or at least almost equal the gravitational force. So as you can see here, this makes much more sense. And also, it's important to note that the green arrows here represent the electric field at each location of each piece of top tape. So in conclusion, the values obtained from the line charge model yields closer to the real value, and the real value being the gravitational force, because you remember that the electric force from the bottom tape and the top tape has to equal the gravitational force. And also these estimates differ because using more pieces allows for more precise locations of each position of charge on each piece. So thus, having more partitions would have led the electric force being even closer to the gravitational force.